So design a column in compression, axial compression. So it takes a little bit of thought in it. So my first take would be when I'm looking at my columns. So what, first of all, or what are the boundary conditions? What are the restraining to my columns? So first of all, looking at the boundary conditions, I normally design my columns to be pin-bend connection because the pin at the base, the pin at the top, where the top is going to be restrained by your beams or floor elements is going to be pinned. So it's because it's so hard to make a fixed connection at the base of the timber column. It's just too difficult. So I normally just say, okay, pin the top and the pin at the base. That K10 is 1. And next thing is regarding to my global stability of my column. So what are the restraints and where are the restraints to my column with respect to my major axis and then my minor axis. Here we've got my major axis, the XX. So with they call it S22, that is deriving your slenderness factor, and the S33 is the minor axis, which is Y-axis, that is the slenderness in Y-axis. So S in terms of a major axis in terms of X direction. So what is restraining my column buckling from major axis, which is these outriggers that is protruding the column. So it's spanning between these two. So that would be my restraint to my major axis. So my beam, if is going to buckle, it's going to be like that shape. So that would be the major axis buckling. For y-axis, what's restraining my y-axis are those goods attached to my column. So when you try to bend, it's going to be bent like that. So that's my y-axis buckling shape. That's that. So as you can see, that would be giving that you would work out what is your Lx and Ly depending where your restraints are. And for example, let's jump to here and make some exercise. So say if your S22 is 25 and S33 is 35, and by looking at this graph here, and you can work out your 25 is something over here, and it's a dry timber, and that would be your SK8 factor. It's roughly about 0.43, call it. And then your S33, that's a minor axis slenderness, so it's going to have like a triple curvature. So that's a 35. So we'll be looking at here, they kind of cross and over. So you get about, okay, 0.25, whatever. So your minimum value of that slenderness gives 0.25. Then that is your K8 factor. So 0.25. And then you factor it in, and it gives you, eventually gives your axial compression capacity. Just to be aware of that, your FC is the compression characteristic strength, compression parallel to grain. You barely have, well, it's not common to have a column in loaded in a perpendicular manner. It's rare, but just pay attention to that. Your column's compression capacity is higher than your perpendicular, because when you try to compress your column, for example, these fibers, if you have like a perpendicular to grams, it's much easier to compress these layers of fibers, isn't it? But when you have this compression that's loaded axial, and these forces trying to buckle these fibers, so these fibers will be buckling, trying to think of in the microscope. So this will takes a lot of effort. So that's why the compression parallel to grain is always higher than perpendicular to grain. So that's just bear that in mind. Yeah, so that's the columns in axial compression. Just be aware of your slenderness and your compression characteristic strength, whether it's perpendicular or parallel. Yep. Thanks for watching.